Well, we've got ourselves a nice little formula here to use. So I'm going to move some things around here. I'm very interested in this DS thing right here. Now remember that segment length? It's not really popular, right? So what is a DS? So I'd like to do is manipulate that a little bit, and let's see if we can work that out. Now we actually know that if we look at radian measure, thank God that we've got ourselves those math people to help us out with these things. So if we remember, the definition of a radian is the angle in radians is going to end up being the arc length divided by r. So if we look here, we can actually take this, and let's say we want a little bit of change. So d theta, let's say that little change in angle is going to be the result. We're going to end up with a little bit of r, ds divided by r. Now why doesn't the radius change? Well, if you look around there, a little thin, small angle change doesn't really change the size of the pizza. You know, when you order, you get a certain size, small, medium, or large. When you swing around to actually get the pieces and how large the slices are, it's not changing the size of the pizza. It just changes the size of the piece that you get. All right, now let's solve this for ds. So we end up with ds is going to be equal to r d theta. All right, now let's make our little substitution in here. I'm going to rewrite this. So I've got dE is equal to 1 over 4 pi EO lambda and r squared in the bottom, looking good here. I'm going to put the cosine in here, and then ds. Instead of writing ds here, like I did, can I replace the ds with, and it looks like we've got r d theta. So I'll put r d theta, which is kind of nice. Now we can manipulate. We've got an r here, and we've got an r squared in the bottom, so we can get rid of one of the r's, so we end up with just the r in the bottom. So let's clean this up. So we have dE is equal to 1 over 4 pi EO, all right, epsilon naught, and then we have lambda, and then cosine of the angle, d the angle, like so. Now remember, we're using radian measure. And finally, we have an r in the bottom, and r is a constant. All right, now let's take a look at all our things here. We've got ourselves 4 pi epsilon naught, constant, constant, constant. Lambda, the density, we know the density of the charge density is not going to change. We've got some symmetries there. R is the radius. If we look from point P, how far is it to the arc all the time? There's a radius here, no change. Here in the middle, no change. From here to there, no change. The r itself is also constant. Okay, so these are all our constants. We group them nicely. Now, what does change? The angle changes. So when we do our integration, we've got our constants here, and then when we integrate to get our electric field, we've got just basically to find the derivative of the integral of the cosine. And that's what we got. Now, let's take a look at our boundaries. All right, we're going from, let's say, negative 60 to positive 60 degrees, like so. All right, now, one thing to reconsider here. All right, when we started to do d theta and we started this manipulation, were we using radians because it's actually an arc? So this was nice because the radius didn't change, and when we did the angles, if we used right triangles, it just doesn't fit this problem because isn't everything swinging in an arc? So if we're using radians here, when we set these boundaries, we also have to use radians here. So what I would try to do at this point is convert these into radians. So instead of saying 60 degrees, it's actually 1.047 radians. Well, big deal. I mean, 60 degrees or 1.047 radians is the same thing. All right, and then here we've got minus 1.047 radians instead of saying negative 60 degrees. Now, when we go to evaluate this, we use these numbers in our evaluation, not 60 or negative 60 degrees, because we're actually using radian measure. Now, if we go back through this, I mean, if we continue with this problem, it should be relatively easy for you as a calculus person. All right, so of course the integral of dE is going to give us the electric field. Isn't that what we're looking for at point P? And then when we look here, we know that if we go to integrate this, the integral of the cosine function is going to end up being Well, let's see, cofunctions, aren't they negative? So it's going to end up being negative sine of dE of this. So the answer is going to end up being a negative sine of the angle. All right, plug in our boundaries like so, and now we can solve it. Now, there's one last thing to consider. All right, as we look through this and when we evaluate this and put sine here, make our evaluation, whatever it is. Now remember, this is a definite integral because we actually have some numbers here. All right, is there anything that we can do with the density, lambda? And the answer is, well, yeah, I guess we could, you know. So if we go back there, what is lambda? So as we go back in our evaluation here, isn't the original charge probably what they're going to give us? So they're going to say, we've got a ring with 20 microcoulombs of charge on it. Boom. They're going to give us big Q. Well, if we got that, that's kind of nice. All right, now, we also know that we have an arc, and the arc is only 1/3 of a circle, this length here. Can we make a substitution now for lambda in terms of charge and the radius of that here in our factors right here? So, as we replace the lambda with this part, evaluate it using the sine, etc., we should be able to solve this problem nicely. So when you come into class, and I have a half a sheet of paper there, I would think that you at this point in your career would be able to evaluate this and then get a final answer using this combined with this and then with the integral. So I wish you the best. Be prepared when you come into class and you've worked this all out ahead of time, and then you walk in and you've got yourself some easy credit.